Alrighty. So, we have quite a few topics to talk about today, so I'm going to try to be quick working through it. But first things first, we're going to be talking about resting membrane potential. And so I'm going to be drawing stuff and I'm going to reference the whiteboard um, once I'm done drawing. And so let's explore how neurons communicate through electrical signals. And we'll start with resting membrane potential. And then we'll move on to action potentials, ion channels, and the role of myelin, which is very important. So a neuron at rest has a voltage difference across its membrane, and that voltage difference is usually around negative 70 millivolts. And this is due to ion gradients and selective permeability. So we're going to talk mainly about these ion gradients, okay? Guess you can't really see that too well. So we're going to have a membrane, and on the inside of the membrane, we are going to have a net negative charge, and on the outside, we're going to have a net positive charge. And this, I'm going to use red to indicate our potassium, which is found inside the cell. Okay, we're going to have a lot of potassium inside the cell, so I hope you can kind of see that here. And we're going to use blue to indicate chloride. We're going to have a few of these chilling outside of the cell. Okay? So those are our chloride ions. And then we're going to have our sodium ions, or Na plus ions, and I'm going to indicate those as green. We're going to have a lot of these outside the cell. Okay? Now this isn't what our cell membrane looks like in resting potential. This is just what it looks like right now when I'm explaining it. And so now we're going to talk about a few tools that our membrane uses to maintain its resting membrane potential. Okay, so we're going to talk about sodium leak channels and potassium leak channels and a sodium potassium pump. We're going to indicate the sodium and potassium leak channels as just the gap. We're going to put one right here and one right here. Okay. Now for one of them, we're going to label it as the potassium leak, and the potassium leak channel is going to show these potassium ions leaking out. And we'll talk about the significance of potassium leaving the cell in just a minute. And then we're going to have the sodium leak channels come. Oh, that's a wrong green. We're going to have the sodium leak channels push sodium into the cell. Okay? And then the last pump we're going to need to talk about is a sodium potassium pump. Okay, now this requires ATP because it's going against the gradient, right? And so we're going to show 3 sodiums moving out of the cell while 2 potassium are going to be moving back into the cell. Now this is really important because the potassium naturally wants to leave the cell, and the sodium naturally wants to enter the cell. And so the reason why this is counted as against a gradient is because it's going against the norm. It's going against what the sodium and the potassium want. So that's why it requires ATP. And if we were to measure the voltage here, it would be negative 70 millivolts with a voltmeter. Okay, and so this is what a typical cell membrane looks like with all of these pumps. We're going to talk a little bit about this and how it correlates to the Nernst equation. So I'll write the Nernst equation down here, and I'll continue to use this um, as we go. Sorry, I'm just referencing some notes. And this is the natural log of the concentration. Then on the outside, over the concentration of the ion on the inside. Okay, so Nernst equation calculates equilibrium right here of the equilibrium potential for each ion. Okay, and we're also going to be talking about driving force, which helps us understand this equation. Okay, so driving force, in this case, the driving force is going to be the sodium because the sodium wants to come into the cell, and that's going to produce a larger charge, one, and the potassium's leaving the cell, and that's less forceful. Okay, then the driving force, which is inward. The driving force is always going to be inward. Okay. Now, we're going to talk about some things that affect resting membrane potential. So obviously something that affects resting membrane potential is going to be the concentration of ions found within the gradient, right, found within the membrane. So that's going to affect our resting membrane potential. Selective permeability, so these channels and the pump are going to affect our resting membrane potential, and the sodium potassium pump, which is just, it's different than the channels because it's pumping against the gradient. And obviously temperature is something found within the body that can affect it as well. So that is resting membrane potential, which leads us to question and talk about what happens when we're not at rest and how do we dictate that. And so I'm going to draw a little graph here that we're just going to use to explain some things coming up. Okay, so on the x-axis we have time, and on the y-axis we have electric potential. And I'm going to label some important concepts here. So I'm just going to draw it out and then I'll talk about it. Okay. So this is what we call an action potential graph. Okay. Now on the graph we have, on the x-axis we have time, and on the y-axis we have electric potential, or membrane potential. Now on the graph this ranges from negative 80 to positive 40 millivolts. And something I want to point out here is that our resting potential is negative 70 millivolts. So we see that right here as a resting potential, and right here as a resting membrane potential. Okay? And now a few things to point out. Resting membrane potential, rising phase, falling phase, hyperpolarization phase, and then after hyperpolarization. Okay? This is the threshold. This dictates how the ATP behaves. Okay, this is the peak. This is the maximum amount of charge we're going to get in an action potential. This is repolarization, so it's going back down to the resting potential, passing through the threshold. This is hyperpolarization, and then this is refractory period, and we'll talk a little bit about that. First, I want to talk about what exactly is happening within the membrane to produce such a steep rise. So I'm going to draw a zoomed in um, membrane again with some pumps here. Okay, so this is how they drew it in class. So we're going to draw sodium with green, and the sodium is going to be rushing into the cell. Okay, so here we had our resting potential. Okay, at our resting potential, we had fluid movement of ions, and our membrane potential was negative 70 millivolts. Now, when we are in the rising phase, our sodium, our sodium channels are opening up, and sodium ions are rushing into the membrane or into the cell. And that's going to cause depolarization from negative 70 millivolts all the way up to positive 30 millivolts or positive 40 millivolts. So it's when the threshold is reached, our sodium channel opens, causing rapid influx of sodium, and then our charge will increase as well. Okay, and now we're going to talk about the falling phase. So I'm going to draw another set of pump, but this time these are the potassium pump. Okay, and I'm going to draw the sodium pump is closed. Right. So for the falling phase, we have the closure of our sodium pump, and so the little ball plugs up that hole again down there, and it's inactivated. Now and then for the falling phase, we have the potassium pump opening up, causing potassium to rush from inside to the outside of the cell, and that's going to cause a steep and rapid dip and drop into from positive 30 millivolts to far below negative 70 millivolts. And now we're going to talk about hyperpolarization. What ends up happening is we just flood the outside of the cell with potassium, and this is going to cause a potassium efflux, and it's going to dip farther than negative 80 millivolts here. So potassium continues to leave the cell, briefly making the membrane more negative than the resting level. And now we're going to talk about refractory period, which is right here and right here. So I'm going to label some things, and I'm going to go with blue. So dark blue is something called absolute refractory period, and the light blue is going to be called relative refractory period. Okay. The dark blue, from the peak all the way down the falling phase through hyperpolarization all the way back up to the resting level is called absolute um, refractory. During absolute refractory period, no new action potential can start. Okay, and then the light blue is the relative refractory period, and in this refractory period, only strong stimulus can trigger action potential. So there might be an opportunity for an action potential to happen. We're going to talk about the difference between graded potential and um, we're going to talk about the difference between graded potential and action potential. So I'm going to start by drawing a neuron with the soma. We're going to start by drawing half of the soma and then a small portion of the axon. Okay. Now, just like the other one, the soma is going to be negative charge, and the outside of the cell is going to be a positive charge. And inside, we're going to have a stimulus found inside of the cell, okay, inside of the soma or a dendrite specifically. And it's going to cause a graded potential or electrical stimulus, okay, an electrical um, kind of force. Now, this is the stimulus up here. Something happened to cause a graded potential stimulus within the soma or dendrite. Then it's going to emit waves of this, stimulus, okay? And that's going to open some ligand-gated channels for potassium, or for sodium. So sodium's going to be rushing into the cell, causing a electrical difference, and that's going to push a force this way. Okay, and so it's going to be a smaller, even smaller, and then gone. So this isn't very strong. This depolarization wave isn't going to be very big. The amplitude of this varies and can be depolarizing or hyperpolarizing, and it fades with difference. There's no threshold. So there's some pretty specific things that we need to recall. So if we were to hook up a voltometer for this, it would show a small change in charge. So from negative 70, our resting potential, up to about negative 60 millivolts. So it's not going to be very big. Now we're going to draw an action potential found within an axon, not in the soma. So I'm going to draw this a little bigger with a couple myelins so we can knock two birds with one stone. Okay. So, a key difference for this specifically, the difference between graded and action potential is an action potential is like a spike. It's either all or nothing. You don't get a decay, okay? And they're always identical in size and shape. So we're going to illustrate this by having sodium rushes in, it depolarizes the cell, and then sodium channels open up, and sodium is rushing out, and it repolarizes the cell. If we were to hook up a voltometer for this, it would show, all of it would show the same spike, negative 70 to plus 30 millivolts. Then it would go down to 80. So it's just our action potential graph that we saw before. The threshold is approximately at negative 55 millivolts. The location is in the axon instead of the soma or dendrites, and it is only depolarizing. the action potential is only depolarizing. The graded potential is both depolarizing and hyperpolarization. So that's some pretty distinct key differences. I need to draw this out really quick. I got distracted. Okay, so I'm drawing two channels and a pump. Okay, so we're gonna have sodium and potassium. We're gonna have potassium rushing out of the cell, sodium rushing into the cell. And with the pump, we're gonna have it going across the gradient and trying to get back to resting potential. Okay. And so this is what it looks like. Each myelin is this bulb right here. Okay, and in between is each node of Ranvier, and this is where all the fun happens, all the biology happens, okay? So right here is where the action potential ignites. Okay, and then it gets shot down here, and the waves are the same size and shape throughout the entire axon. Okay, and so this is our force, and it's going this direction. As potassium leaves, as sodium enters, we depolarize. Okay, and then as potassium leaves, we repolarize. So much so that we hyperpolarize and we go back down. Okay, and so this is what an action potential looks like. Found within. Let me go back up really quick, and I want to expand some of our vocabulary here. So capacitance and length constant is what I want to touch on next. So capacitance is the membrane's ability to store a charge, whereas the length constant tells us how far a signal can travel before weakening. I'm going to write down an equation. It's lambda equals radical Rm, which stands for membrane resistance, over Ri, which is internal resistance. And to understand capacitance, we need to understand that capacitance is the ability to store a charge. Okay, so a higher capacitance equals a slower response. So we want capacitance to be smaller. Now, right here, there is no membrane resistance. Okay, nothing can go in and out of our membrane when there's a myelin. But when we're in a node of Ranvier, there is a ton of membrane resistance, and that is because we are bringing sodium in and potassium out, and vice versa with the sodium-potassium pump. And when we're in the region where the myelin is, we have no membrane resistance, and so we have a higher length constant. It's the same for the internal resistance. Since we have myelin, the internal resistance is minimal because our axon is typically bigger. Whereas up here, this one doesn't have any myelin because it's a smaller neuron. The larger neurons will have myelin to speed up this concept. So a short length constant means a fast decay, whereas a longer or larger length constant number is a slower decay. Alright, and so myelin reduces capacitance and increases resistance, allowing faster signal travel and increasing the length constant. So again, up here with an unmyelinated axon, our signal will fade significantly faster because we have more membrane resistance and more internal resistance. Okay, now a myelinated axon has signal jumps between nodes of RON-VA. So we have less resistance in here, and so we're going to increase our speed as we go. And this is going to propagate our action potential, causing it to travel a larger distance. So lower capacitance, higher membrane resistance, and faster conduction, right? So resting potential, if we could sum everything up, I could say resting potential sets a baseline, while action potential transmits signals. Capacitance and myelin shape how quickly and how far signals can travel within the axon. So I hope that explains everything, and thank you for watching.